So today I'm going to talk about a framework called Learning from Aggregated Data, and this is based on two papers that have been in collaboration with folks at Google Research, with Lynn, Matthew, Ashwin, Thomas, and Vahab. Okay, so some of you may have already know about this framework of data aggregation, but let me try to motivate that a little bit and set the context, and then see what are the results that we have. So in the vanilla supervised learning problem, the setting is that you give a training set to the learner. The training set consists of n samples, and each sample is a pair of multidimensional feature vector xi, and a response or label variable yi, depending on whether you have a classification or regression problem. And what the learner wants to do is to fit a model to this training data that can be used for prediction. So this is the usual supervised learning problem. In the weakly supervised learning problem, the learner doesn't have access to the individual labels. Instead, you want to give some aggregation or some summary of the labels over the set of samples, which are called the bags. Okay? If it's a classification problem, then this summary could be, for instance, label proportion. Now, the setting of weakly supervised is relevant in very diverse application. I think the paradigmatic example dating back to many, many years ago is for election process. What people do is that you don't want to reveal the individual vote for the candidates. So what you do is that you just reveal the aggregation of the votes at district level. So district here would correspond to the bags that we have. The other example that's well known is in group testing, where you have scarce resources and you want to chase something in your population. Maybe it's a disease or you have a quality control problem. And instead of trying to test each of the samples separately, you combine them together and try to test these aggregated samples, okay, to be more efficient. There are other examples in high energy physics. So I'm not an expert on this one, but what they try to do in high energy physics, they want to classify the event coming from two possible originating process. So the example that these guys discuss in the paper is if you want to classify like quark-induced jets from the gluon-induced jet. And apparently what happens is that the discriminants for gluon versus the quark is very poor, but it's easy to understand the label proportion, the frequency of each of them in a given sample. And the other example is in radar image classification, that you want to have rapid data acquisition. So instead of trying to label at pixel level, you want to label at like grids in the image. Okay? So these are the examples that the learner doesn't have access to the individual responses. Some of them is because getting the individual labels is expensive. Sometimes you don't have the technology. You don't have enough resolution. You want to do it under like some time constraints, so you might sacrifice getting like higher resolution. So it could appear this framework of aggregate learning for different reasons. And I would say that recently there has been a resurgence in this area, mainly because of the privacy concern. So some of the big tech companies are using aggregation as a way to provide some layer of privacy protection. Examples are Apple SKAd networks library and also the Google Privacy Sandbox. And this is the way that I got involved into this framework and trying to understand what's happening in this area. Okay, so what's the problem formulation? Let's come up with some concrete formulation, and then we build upon that. So we are given m disjoint bag of samples, and each bag would be like a collection of feature vectors. The bags could have different size, and then for each bag, I will give you the average of the individual responses over that bag. Okay? The goal is that given these aggregate responses and the individual features, I want to learn an instance level model. So if I give you a future x, I want you to tell me what would be the y, the individual y. Okay? And this is like the picture. Each bag is consisting of, let's say, n sub l feature vector, and then you don't have access to the individual labels, only the aggregation or the average of them. Okay? So there are two important problems in this area. The first problem is that how do you want to learn the model? What loss do you want to minimize? How do you want to minimize this loss? So that's the first important problem. And the other one is that how do you want to construct these bags? if as a learner or like the platform designer, you have like this authority to construct these bags under some constraint that you have, what's a good bag construction scheme? And the usual or the natural constraint that you have in the bags is like a minimum size constraint. So you want the bags to be, let's say, non-overlapping or having very small overlap, and each of them to have size at least k. And this is natural because, as you can imagine, the larger k would give you better privacy because you are aggregating over a larger set of bags. You can try to formalize it in terms of like k anonymity, or as we were discussing in the last talk, if you put some stochasticity assumption on the data, you can try to compute the mutual information between individual labels and the aggregate one, condition on the features, and then show that as k goes up, this mutual information is decreasing. So that would be like a measure of information leakage. Is it differential private? The aggregation, as I say, on its own, it's not differential private, and it's very easy to see that. There is no randomization, right? It's just the aggregation. So towards the end of the talk, I will talk how to make it differential private and what are the trade-offs that we have. But again, it's not always the easiest choice to go with differential privacy because it's a worst case. It's a very strong privacy guarantee. And as Jelani was explaining, there is always trade-off between the model quality and differential privacy. So sometimes in practice, you don't really want to go with differential privacy. If you have legal constraint just to reveal the aggregate data, and you can do that and learn good models, then you are fine. So there is this intricate difference between providing DP or privacy in the strongest case, or just sticking to the constraint, whatever legal constraint that you have. Okay, but sometimes we want to be like make sure that we have the best privacy guarantee. So I will tell how to go with this approach as well. Okay, so the first part of the talk would be on the first problem that I said. How do we want to fit a model? And for this one, so there are two problems. I want to decouple them. So in the first part, I go with random bagging. I just randomly partition the data into size of bag k, and then see how we can fit a model. And then in the second part, I fix the learning process and then discuss how to form the bag. So these are decoupled. It would be good to have something that's unifying, but for now we have this decoupled result. Okay, so there are two popular approach, or I would say loss functions, that you can try to learn a model given this aggregated data. The first one is called instance level. So we have the individual features, but you have the aggregated labels. And what you can do is that you can try to match this aggregated label to each of these individuals in the bag. Okay? So it's the usual empirical loss minimization, but I'm using the average response for all of the individuals. Okay? But for each of the instance, you basically have a term in this loss function. Okay? The other one is what we call the bag level loss. So instead of trying to fit the aggregated labels to each of these guys, I have a predictive model f of x, so I can try to come up with the aggregation, the average prediction that I have over these bags, and then try to fit y bar to f bar. Okay? This is bag level loss because for each bag you only get one term, the loss between these two, right? And there are many other ways, many other loss functions in these areas, but these two arguably are the most common ones. And we've been trying to test these two loss functions along a couple more on some real data set. And it was happening that this loss was working much better than the instance level. But we were not sure whether it's always the case. What's the relation between these two? What are the trade-offs here? So we wanted to develop some theory, even for some very simple models, but get some insight on what's the connection between these two. Okay, any questions so far? Okay, so I'm going to give these two loss functions some names. So the first one, I call it instance level. And the other one is the bag level loss. And the first result, it's very simple, just I would say calculus exercise, is that if you have a quadratic loss, so if your loss function L here is quadratic, then you can write the instance level loss as the bag level loss plus the regularization term. And what's this regularization term here? It's basically the variation that you have within each bag. One thing that you might note is that the term regularization often is used when it's data independent, like L2 norm of the model or L1 norm. This one depends on the features, but not the labels. So it's sort of a data-dependent regularization. And it's also common in learning theory. So these are some of the examples that people work or use the term regularization, even it depends on the features. Right? The second thing is that, OK, so before I go to the interpretation of this one, so this was for the quadratic loss, but if you go with like a general loss function, as far as it has like a bounded second derivative in the second argument. So this was the response argument. If it's bounded and like continuous, then you can show that this is an upper bound with some constancy. Okay? So it's just like a Taylor expansion, and it's very easy. But so you have the same thing, but it's an upper bound. Okay? But what would be the interpretation of this one? If you have a regularization term here, the first implication is that, OK, if you try to learn a model by minimizing the instance level, because of this regularization, you probably have a bias. But you have more stability. So the variance of your estimator, the model would be lower. But if you go with the bag level, probably the bias is lower, but you have higher variance. And the bag level, again, recall that we have only one sample per bag. So you have n samples, but only you are forming a loss over the bags. So your effective number of samples is much smaller than n, right? So because of that, the bag level would have a higher variance. Okay? So we want to formalize this intuition and see whether it's true or not. And the second one is that once we have the form of this regularization from the quadratic loss, how about keeping that form and then trying to play with the magnitude or the effect size of this regularization? So instead of having just R of f, I want to put some coefficient rho. And then you can try to tune this rho, let's say, by cross-validation. Or if you have some theory, it tells you what would be the optimal rho. Okay? So we call this one interpolating loss because if rho is 0, you have the bag level. If rho is 1, you have the instance level. And then you have like a continuous transition from the bag level to the instance level. OK, so let's, as I said, we will focus on something very, very simple, a linear model, a linear regression model. But it's already rich enough that tells us the intuition that we have, the bias variance trade-off. So the usual linear regression model, the data model is that you have n pairs coming from the linear form. Xi are IID Gaussian, and the noise is also 0 mean and variance sigma square. And then we consider a proportional regime where the sample size and the feature dimensions are growing at some, like, let's say, proportion. So n over d is going to some constant. This constant is arbitrary, but should be fixed. It could be less than 1, or it could be very, very large. So you can cover like under-parameterized to very over-parameterized regime, but n and d should grow at the same rate. And you can say why I'm thinking about this regime, because if n was much, much, much bigger than d, then the variance was small. So if I want to see the bias variance trade-off, I want to go with this setting to get a good understanding of them. The bags are of size k, and k is fixed as n and d are going to infinity. The norm of the model, theta 0, we can assume it's constant, so you can just rescale everything and say it's 1. And as I said, for this part, I'm assuming that the bags are formed like randomly. So they are of size k. Yeah.
So it doesn't cover n less than d, right?
Yeah, so this one, like, yes, for the part that I'm going to present, we want it to be bigger than 1. But if it's less than 1, then we have another.
How does k scale?
K is fixed.
Is fixed.
K is fixed, and n and d are growing. Any other question? So I said the bags are random, but what I really mean is that it's independent of data. So if you have some, I don't know, other data set that the bags are constructed, based on those, you can still apply this. Okay, so what I want to do is to understand what would be the model risk, and then what are the dependence on the size of the bag, the over-parameterization that you have, on the signal-to-noise ratio in the model, like how strong your model is compared to the noise. So I want to capture those effects in the risk that I have, and then see what are the trade-offs I get. Okay? So conditioning on the feature vectors x, this is like the model risk that I have, and then I decompose that to the bias and variance term. The first result that we have is on the bias characterization. So in the proportional limit, you can exactly characterize what would be the bias of your model. And you see that it depends on psi. It depends on the size of the cluster. It doesn't depend on signal-to-noise ratio. So I was assuming that the norm of the model was 1, but you still had the sigma squared, the noise. It doesn't show up here, so it doesn't depend on that. And it also depends on the row, how you are trying to balance the bag level versus the instance level loss. So this is for the bias, and then you can also get a result on the variance. So we can precisely characterize the bias and the variance component under the linear regression model. Okay?
So is this by minimizing the bag level loss or instance?
This one, OK, so this would be for any row. So if row is 0, that's the bag level. If row is 1, is instant level. But for any row, you get the characterization. Okay? So you can try to use this result to see what's the optimal row, what's the optimal tuning. Right? You have the analytical form for the risk of the model. So these are some synthetic experiments. The first thing is that the experiments are in very great match with the theory. So D here, I think, is 100. But you see that these solid curves, these are the theory, and then the dots are like what you get from the actual experiment. So D is only 100, but you already have a good match for the asymptotic theory. And then the x-axis is row. So you see that there is some optimal row, for instance, here or here, that minimize the model risk. So the optimal row is not at the boundary 0 or 1. It's at something in between. Okay, so potentially you can come up with the models that are working better than either the bag level or the instance level. And then you can capture the effect of different things like the SNR, which is model over the sigma, and then overparameterization, the size of the bag, and you see how they are changing the loss. So it's very natural because as you increase the size of the bag, you see that the risk is going up. So K, the larger K means that your risk is higher, which is what we expect. The other one is that psi is n over d. So if you have larger psi, it means that the number of measurements that you have per feature dimension is larger. So if psi is larger, then the error would be smaller. Like psi equal 8 is the smaller. And the other observation is that if I compare the endpoints of these curves, so this guy, the left endpoint corresponds to the bag level. The right one is the instance level. Sometimes the bag level is worse than the instance level, but sometimes it's better. Okay? So the first experiment that we say we learned that the bag level is always better, it's not true. It really depends on the parameter of the problem that you have. Okay? One question that we were trying to answer is that when the instance level, the model that you learn from the instance level, have a lower risk compared to what you get from the bag level. Okay? And it turns out that you can write a criteria in terms of the SNR. So there is some threshold that if SNR is less than this threshold, this model is better than this. And if SNR is bigger than this threshold, it's the other way around. And the intuition here is that if SNR is low, it means that you have too much variation in the data compared to the strength of the model, right? So the variance is already high. It's better to go with the loss functions that bring down the variance. So regularization here becomes more effective. And we learned that the instance level has the maximum regularization, so it gives you a better risk compared to the bag level. But if SNR is large, then it means that your variation is not that effective, that much. So it's better to focus on the bias. Bring down the bias, and in those cases, the bag level loss would be better. Okay, so you can make, once you have the result, then you can try to come up with justification and whether it makes sense or not. Okay, sounds good? Any question?
So this is a realizable model, right? So you have a theta that is generating this data.
Yes, so this is a realizable model.
So what about the parameter error? Can you say similar things about it?
If the model is not realizable,
I mean, you do have a theta 0 that is actually generating this, right?
yes. So if it's not coming,
you,
let's say data is not coming from linear model or.
No, I'm saying like, but can you give some parameter error guarantee instead? So this risk is just L2 from
the theta.
theta 0. Oh,
yes.
okay. So then
Yeah.
I think that's.
Yeah.
I thought this is the excess.
No, it's just from the theta. Okay, so that was the first part that I wanted to talk about, the instance level versus the bag level one. And the second part is that I want to fix the learning process and then discuss how we can come up with a good bag construction, given like the minimum size constraint that we have. Okay, so that would be an algorithm called prior boost, which is an adaptive algorithm to come up with the bags. Okay, so I'm fixing the learning process to the instance level. Okay, so I'm using y tilde L for each of the instances in the bag, so that would be my learning loss. And then I want to see what would be a good construction for the bags. Okay, and again, I don't have access to the individual labels. I only see the individual features, so how can I curate the bag based on those? Okay. So the high-level intuition is that the good bagging schemes are those that the aggregate response is very similar to the individual response. Okay? So if I had somehow the individual response and wanted to construct the bag, then based on this intuition, what I should do is that I should just put all the samples that have similar responses together in the same bag, right? Because this way, once I take the average is closer to each of the individual responses. Okay? But the problem is that they don't see the individual responses. So the idea is that try to use some prediction based on potentially some available prior. And once you have those predictions, try to combine these samples together based on the predicted labels that you have for them. Okay? Now, what about the prior? How should I know this, let's say, conditional expectation of the response given the x? So there is some probability distribution under this expectation. So I call it a prior. But do I have this prior? What if I don't have any prior on the data? How can I come up with it? So sometimes this prior is available, like it's coming from the domain knowledge, or maybe you have some public data set that's very close to the data set that you have, and you can try to use that data set to come up with some predictive model, and based on that, you cook up this prior for your own data set. Sometimes you can do transfer learning. So you have two tasks very similar. One of them is less sensitive. So let's say one of them is like click-through rate, the PCTR data that you have. The other one is the conversion, the actual behavior, whether they purchase the item on the website or not. Now, the PCTR is not as sensitive as the conversion one. Now, you can use the PCTR to come up with a model, and then use that model to predict the conversion rate, and based on that, do the bagging for the more private, more sensitive task that you have. But the last one that we want to make sure that you can always use this idea is doing something called prior boost, that you start from random bagging, and iteratively you improve the prior that you have. And based on this prior, you improve your bagging construction and the model that you can learn. Okay. Okay. Again, I would start with the linear regression and then go to the GLM models. So in the linear regression, again, I write everything in metrics form. So it's y equal x theta star plus noise. And x is n by d. N is the number of samples. D is the number of features. I'm going to use a matrix S that essentially encodes my bagging construction. So S is a matrix m by n. And I want to optimize over the choice of S. But again, you don't have access to the individual labels. But based on this prior information, how can we optimize over the matrix S? Okay. So how do I come up with this matrix S? It's mostly 0. whenever sample I belongs to bag L, I have a non-zero entry, which is 1 over the square root of size of the bag. Okay, so this is just a normalization. Now, the norm of each row is going to be 1, right? Because each of them has exactly, like the first one has B1 number of samples. And since the bags are non-overlapping, the rows are orthogonal. So S transpose S is like a projection, orthogonal projection. Okay? But it kind of encodes the bagging structure that they have. Okay? Now, I was going to minimize the instance level, but for linear regression, you can write something very simple. It's a L2 norm, and then using this matrix S, you can write it in a simpler form. So if you look at S times Y, what it does, modulo the normalization, is just adding the responses in each bag. So it's like the aggregate response. And when you hit that by S transpose, it's going to lift it and use the same aggregated response for all the instances in the same bag. Okay? And then we want to minimize this loss. Okay. So for the linear model, you have this exact bias variance decomposition. And in principle, what we need to do is to optimize over S here. Try to minimize the risk over the choice of S. So S has some specific construction. It should be of the form of like a, what I said, the projection matrix with 0 and 1 over root BL type of thing. But given those constraints, you want to, in principle, minimize this risk over the choice of S. One thing that we know is that we don't have access to the Y, but we are assuming that there is some prior that gives you this sort of the conditional expectation. So I call it a Y tilde that's approximating this one. But for linear model, this is X theta star. Okay? So I don't have the individual labels, but if I assume that there is some prior and some oracle that knows this conditional expectation, this is like all the information we need here. Okay? Now, in practice, you don't have the exact prior. You're going to approximate that, but you just use the approximation instead of X theta star. Okay? One thing that I want to do is that this optimization over S here is complicated. So I do one step upper bound, and then I try to minimize the upper bound. And hopefully it gives me some sensible guideline on choosing yes. Okay? So if I do this one, then I just need to optimize this. Okay? Now, if you look at the first term, the S transpose as minus I times a vector, this is, you can write it in terms of a clustering objective. Okay? What's trying to do is that it's computing the L2 squared distance between each of the Y tilde I with the center of the bag that you have. Okay? So it's just a clustering problem. So you want to bring down this loss, and then the other term is coming from the variance term. So we already have a trade-off here that was quite subtle before analyzing the linear regression. And that's the choice of M, the number of bags that we have. Okay? So here, if you go with many bags, the first term is going to go down because each of the bags would be smaller. They're non-overlapping, so the distance to the center of the bag would be smaller. So if I increase the number of bags, then this term would go down. But this term would go up. Why? Because if you think about the variance term, larger bags are better. You are aggregating over a larger set. So the variation in the aggregate responses becomes lower if the bags are larger. Okay? So we have a different trade-off here. But the examples that we were looking for these problems are the cases that the number of bags, which is n over k, is bigger than the number of dimensions that we have. And once you're in this regime, you can see that this minimum is achieved by D. So it's independent of M or a bagging construction. It doesn't have any impact here. And you can completely drop this term. Now, if we do this, then you just have a one-dimensional minimum size k-mean clustering problem. Okay? This is the very high-level intuition that we had from the beginning. If you have some approximation of the individual responses based on the prior, you just need to sort them and then put them into different bags, but each of them should be at size at least k. So this is a very simple structural property of a one-dimensional K-means problem. It's very easy to see that if you try to solve this problem in one dimension, it's just sorting structure and then grouping them together. Okay? But still, you need to see what are the right location for these barriers to construct the K-mean. And you can write dynamic programming and solve it very easily. The complexity would be n times the size of the bag plus n log n. Okay. Sounds good? Okay. Now, if we go with more complicated model, let's say generalized linear model, you can essentially follow the same thing. It's just more complicated math. So let's say instead of the loss function, the L2 loss, I go with the log likelihood, but I don't have the individual labels. I just go with the aggregate labels or aggregate responses. And theta hat would be the minimizer of this loss. Okay. The common trick is that the risk of this model can be related to the size of the gradient of the loss at the actual parameter. So if this one is small, it means that the minimizer of this, where the gradient is 0, would also be close to theta star. But if this gradient is large, then it's hard to argue between them. Okay? So the common technique is that you can relate this one to the size of the gradient of the loss at the actual theta star, and then you can do the bias variance decomposition, but it has like a more complicated form. Okay? And you do the same thing. The upper bound is given by this. The first term, we realize that it's already like the one-dimensional K-means that we had. Mu is like the conditional expectation. And the term that appears in the variance depends on the second moment of the responses given x. So if you have the prior, in principle, you have both mu and v. But what happens is that if m over d, m is the size of the bag, it's n over k, and d is the dimension. If this is bigger than like the ratio between the maximum to minimum value of vi, which for many of the common models, if you have like bounded features, everything, this is order 1. So if this is the case, then you can drop this term. The minimum is achieved by this guy. And then it becomes completely independent of the choice of the bags. Okay, so you can completely remove the second term if you are in this regime. If not, then you need to do more. You need to work with both, the first and the second moment. But if you are in this regime, then this will go away, and you just do the K-means using the first moment, based on the prior that you have. Okay, sounds good? Okay. Now, do we have any theoretical guarantee that this approach using the prior is better than random bagging? So the first result is, again, for linear model, but if you do, if you use the prior in constructing the bags, the upper bound that we get would be of this form. So you see that the first term is coming from the bias. It gets worse with the size of the bag. The second term is the variance. But the interesting thing is that as you increase the number of samples, both of these terms, the bias and variance, are going down, because you are actively trying to put individuals with the same response together. And this way, you are trying to minimize the bias. The bias was the K-means objective, basically, right? But if you go with the random bagging construction, we get this lower bound. So this would be the bias and the variance. And this lower bound, no matter how many samples you have, so if n is growing much, much larger than d and k, this term goes to 0, but this term goes to 1 minus 1 over k theta squared. So you always have a bias. If you do the random bagging, no matter how much you increase the number of samples, because you don't actively try to minimize the bias, you always have this bias term. And so your risk doesn't go to 0. But this one, the risk can go to 0 as you increase it. Okay, sounds good? Okay. So the last part that I want to talk is something called prior boost. So this is when there is no prior available. How can you come up with a good prior iteratively for constructing the bags? And this is the way the algorithm works. So you're going to split the data into t chunks. So for now, I just go with the equal. Whether it's the optimal things, or maybe I should increase the size of the chunks like logarithmically or in some other way, I don't know. But let's say the simplest one, I just equally partition into t groups. On the first part of the data, I just do the random bagging. I construct a model based on that, and then use this model to come up with the bagging construction on the second part of the data. Okay, so once you have the model theta hat 1, let's say, in the next step, you go with the second chunk of the data, you have f of theta hat 1. So that would be like the predicted labels that you have, and then you run the k-means on those. You put them in the bags, and you do it over and over. So I never use the individual labels. I only use the aggregate labels. And I iteratively improve this prior to come up with better bagging construction as the iteration goes on. Okay? And at the end, you give like theta hat of t. Okay. Sounds good? Any question on the algorithm? Okay, so how does it work in the experiment? So here I'm using a linear regression task with different choices of k. The dots are if you do just random bagging on the entire data set. So it doesn't depend on these steps because you do it just once. Okay? And the solid one is if you do this prior bus. And as you see, as the number of steps goes on, the MSE of the model starts to decrease. And of course, larger k is worse for your risk, but you are always much better than the random bagging. Okay. Now this is what we had for linear regression. You can do the same with the logistic regression, like binary classification problems with sigmoid. And again, you see the same behavior. Prior boost is much better than just a random bagging. Okay. Okay, so that was on like the second part. So in the remaining time, I want to talk about differential privacy and how you can go from the aggregation to differential privacy. Now, through the talk, I was just working with labels, right? I was just aggregating the labels. So it's like I'm only concerned about the privacy of the labels, not the features. And there's a notion called label differential privacy, which is like just a restriction of the usual differential privacy notion, but in the setting that you only care about labels, not the features. Okay? And I think the first work that introduced was by Kamalika and Daniel in 2011. Okay? Now, aggregation on its own doesn't give you any label DP, but how about adding some randomization on top of that to ensure label DP? So once I compute the aggregated list responses, I can just do the Laplace mechanism. So Laplace mechanism, for those who don't know, it's a very classical method to ensure DP. You just some additive Laplace noise, but the variance of the noise depends on like the privacy budget epsilon that you have, and also the sensitivity of your data to replacing just one record. Okay? So here, if I change one of the responses, one of the individual responses, and let's say the response is bounded by B, the sensitivity would be B over K on the aggregated response, right? Because this guy would be aggregated with K minus 1. So if I change one of them minus B to B, the sensitivity would be B over K. Okay? So I add this Laplace noise, and this is easy to see that this gives you the epsilon DP just by usual classical Laplace mechanism. Okay? But the interesting thing here is that it seems there is a trade-off on the choice of K. Because if I increase K, I have larger bags, so probably the model is not good. It gets worse as I increase K. But on the other hand, the sensitivity would decrease as I increase the size of the bag. So I only need smaller amount of Laplace noise to ensure epsilon DP. So is there a trade-off here? Is there a good or optimal choice of K here? Right? And if I get the optimal choice of K, and it's different than 1, it basically tells me that it's better to first aggregate labels and then add the noise, Laplace noise, on top of it, instead of just adding the noise to the individual labels. Okay? Make sense? So if this was the optimal one, K equal 1 was the optimal one, it was saying that don't do any aggregation, just add the Laplace noise. If K was something other than 1, it means that you should aggregate within some bag and then add the Laplace noise. So for a given fixed privacy epsilon loss that I have here, I want to see which of these approach gives me a better model, or what's the optimal choice of key. Okay? So we studied this only empirically, but there are some nice observations that would be interesting to see if there's a theory for those. So here I'm increasing the number of samples that I have. Different curves corresponds to different size of the bag. And the y-axis is just the log loss of the model. So if n is here, you see that the optimal k is k equal 2, and then it becomes k equal 4. Here it's k equal 8, and then here it becomes k equals 16. So the first observation is that the optimal k is not 1. The second one is that the optimal k is increasing with the number of samples. And also the crossover becomes further apart as n increase. So if I want to guess here, it seems that like the optimal k is going with like log of n, right? And as n grows, so there are some crossover that up to this point, k equal 4 is good, and then k equal 8 is good for a longer next episode, and then it shifts. So this is what we observed, but you can try to justify why this is happening. So I said that there is a trade-off in choice of k in terms of like the bias variance. But for prior boosts, we said that we are trying to bring down the bias with this clustering, right? So as the number of samples increase, both the bias and the variance are going down. But what happens is that the bias is going down at a faster rate. So if n is larger, it means that the variance becomes more important than the bias. And because of that, larger k would be better, because larger k means you are aggregating over larger bags. Okay? But if n is small, then the bias becomes important, so you should go with like smaller k, so you reduce the bias in the estimation that you have. Okay? But all of these are just based on this experiment, and we don't have a theory for that, but that would be nice to come up with like what's the optimal k here. Okay? Any question? Okay, let me summarize what we discussed. So we talked about the framework of working with the aggregated data. This is a framework that has been relevant to many, many different domains of applications, from group testing, from elections, in radar, engineering, and then we also talked about like the privacy protection that it gives and the motivation for this framework from the privacy point of view. We only focused on aggregating labels in this talk. So the features are not sensitive, but the labels are sensitive, and we want to protect the privacy of those. You can think of like more hybrid regime where, let's say, I don't know, 10 of the features are also sensitive, but the other one, D minus 10, are not sensitive. Can I do the aggregation something in between? Not just on the labels, not on the entire data set, but half-half. Okay. Two main problems that we discussed in this area. One was how to learn a model, instance level model. And the other one was how to come up with the back construction. So in this talk, I sort of decoupled them. On the first part, I said, just think about the random bagging, and then the loss functions, we talked about the instance level, bag level, and then a way to interpolate these two. We talked about the bias variance trade-off between them. The instance level was inducing some bias, but it has lower variance, it has more stability. The bag level has lower bias, but it has larger variance because you only have samples 1 per bag instead of 1 per sample. And you can try to optimize this bias variance trade-off. Either you have some analytical formula like the linear regression, or you can do like cross-validation in practice. The second part of the talk was I'm fixing the learning process to instance level, and then talking about how to come up with the back construction using some prior that you could have. Sometimes the prior is given to you from transfer learning or from other public data set, but if it's not, then you can do some prior boost algorithm, starting from random bagging and iteratively trying to improve the bagging construction that you have. Okay? There are many, many interesting problems open here. Like many of the things that I said for back construction was only for instance level. If you go with other loss function, how does it change? It's not clear. What's the optimal k? Does it give you a new way of providing DP instead of just working with the individuals, first aggregate and then add noise on top of that? What's the right trade-off here? So these are like the questions that are still open and interesting. Okay. Any questions?